The Netherlands did not build higher land, it built gates against the sea.
Behind these gates, much of the country lies low and flat.
When the North Sea rises, Dutch engineering has only one job: hold the line.
The first battle was not above the watered Chamberlain, it was on the seabed. Before the gates could close the sea, the Dutch had to build a foundation inside the tide. The Dutch could not build the gates first, Tan Kutru, they had to tame the seabed.
Every pier would stand against tide, storm, and time.
Piece by piece, the barrier moved from land into the tide.
sea had a line of foundations. Soon, concrete would rise from it. The foundations were ready, Sia. Now the barrier had to rise from the tide. The doors arrived by water because the barrier belonged to the tide.
The barrier finally had its shape. Concrete bones, steel doors, and the sea still moving through it.
The barrier had steel doors stoked. Now they had to learn how to move.
Each gate had to drop with precision, then hold against the North Sea.
Each gate had to drop with precision, then hold against the North Sea.
The Dutch did not only build gates, Krian. They built a system to read the water. Now the barrier could move Katahdins. The next test would come from the sea. The barrier was built for this moment, the Code, when the North Sea begins to rise. The gate moved slowly, but the entire delta waited behind it. Outside, the sea kept pushing. Inside, the lowland stayed protected. The North Sea reached the gates Cantalas, and the water stopped moving inland. Morning came, and the low land behind the barrier was still safe. When the storm passed, the gates returned the tide to the delta.
A country below the sea survives by checking every detail.
The Netherlands did not defeat the sea. It built a country.
They did not go around the Alps. They drilled straight through them.
Above, the mountains stood in silence. Below, the railway crossed beneath them.
To connect Europe faster, engineers had to bore through one of the hardest mountain ranges on Earth.
Before the tunnel could cross the Alps, the mountains had to be opened one face at a time.
The Alps were now open at both ends, but the real work was just beginning.
To break through the Alps, engineers first had to read the rock like a map.
The mountain did not move twain for kind, so the machine would have to go inside it.
From both ends of the Alps, the tunnel was slowly eating the mountain from within.
The Alps were no longer just mountains, Kachik. They were becoming a long, engineered corridor for trains.
From both ends of the Alps, the mountain was being hollowed out one ring at a time. Inside the mountain, the tunnel was built as a precise ring of concrete after every cut.
Day after day, the machine pushed a railway tube deeper under the Alps. Deep under the Alps, the railway was becoming a hidden line of concrete and steel. The mountain was no longer the obstacle to Vierd. Now the tunnel had to become a railway. Inside the rock, every meter had to be reinforced for the trains to come. The tunnel was no longer just a hole in the mountain. Note, it was becoming a complete railway system. At last, the mountains no longer blocked the railway crest. The train could go straight through them. They drilled through the Alps tracile and built one of the longest hidden railway routes on Earth.
After years of drilling, the two ends of the tunnel were finally close enough to meet.
At last, the mountain opened into one continuous railway line.
The tunnel was built for trains like this, peed, fast, quiet, and deep under the mountains.
What once took hours over the mountain could now pass quietly beneath it.
They drilled through the Alps hundreds and left behind one of the longest rail tunnels ever built.
The mountain was no longer a barrier. The railway now lived inside it. Deep under the Alps, two perfect railway tubes now cross the mountain from side to side. The Alps still stood above Consmith, but now the train moved through them as if the mountains were no longer there. What once took a mountain crossing became a straight line beneath the Alps. They drilled through the Alps' torrents and built a railway that now lives beneath them.
They did not cross the river, Isuflander. They stopped it. Cross the river, Isuflander. They stopped it.
Behind this concrete, a river became power. Concrete. A river became power.
China built a wall so large, it changed the flow of the Yangtze. Changed the flow of the Yangtze.
Before China could stop the river, it had to build a city of machines beside it.
To build the dam, engineers first had to move the river away.
The temporary wall was not the dam, Hilk. It was the wall that made the dam possible.
For the first time, part of the riverbed became a construction site.
The river was still moving the Popard, but the first dry ground for the dam had been won.
Now the dam began to rise, come tense, not as one wall, but block by block from the riverbed.
Every layer had to cool, settle, and lock into the rock below. The river would one day pass through gates built inside the concrete. The
The river had been pushed aside catatures, and the concrete wall had begun to take its place.
The concrete wall was rising. Now the river needed a path through it.
Inside the dam, the river would turn steel into electricity. The dam could not simply block water in Juliet. It had to control it. For the first time, the river began pressing against the concrete. The river was no longer only flowing, dikacting, it was working.
The Yangtze had not disappeared. It had been redirected through concrete, steel, and power.
The river was no longer wild. It had become a controlled force. Every second, the weight of the river turned hidden turbines inside the concrete.
The dam did not only hold the river, it gave ships a new staircase through the valley.
They did not tear Chernobyl down, that they built a giant steel shield over it.
The shelter was too dangerous to build directly over the reactor, so engineers built it beside the site.
Then they pushed an entire steel mountain into place.
Before the steel arch could rise, engineers had to build the ground that would carry it.
The arch would not be built over the reactor, it would rise beside it.
Piece by piece, a shelter larger than the reactor began to take shape. The shelter rose beside the danger, not on top of it. By the end of this stage, Chernobyl had not been covered yet sieges, but the shield had begun to rise. The shield was rising, but it still had to become a complete machine. This was not just a roof, but tunneled. It was a movable factory built to seal a reactor. The arch had to close around the reactor without touching the danger directly.
The steel shield was complete. Now engineers had to move it over Chernobyl.
The shield was finished beside Chernobyl the 30s. Now engineers had to move it. An entire steel shelter had to slide as one piece. Slowly, the steel mountain moved toward the reactor. Chernobyl was finally covered spacet, not by demolition, but by moving a giant steel shield into place. The arch had moved into place and won the feud, but covering Chernobyl was not the end. Now the steel shield had to become a sealed working chamber. Inside the arch, machines would do the work people could not safely do.
Chernobyl was not erased as passions. It was sealed inside one of the largest shelters ever built. The giant shield was no longer a construction project. It had become Chernobyl's new cover.
Inside the arch, machines could work where people could not. The goal was not to erase the past, but to contain it safely. They could not undo Chernobyl the Smed, so they built a giant steel shield to hold it for the future.
They cut a path between two oceans Proximus and made the sea lift the ships.
A ship did not cross the isthmus, the Sate. It climbed it in stages of water. Cross the isthmus, the Sate. It climbed it in stages of water.
Before the canal, Panama was only jungle, swamp, and the long road around a continent.
The jungle did not give way easily. Every yard had to be taken by machines.
Before the canal could join two oceans, Panama had to be cut open by steam, rail, and mud. And
The cut had begun topine, but the isthmus was still fighting back.
Every meter carved through the isthmus had to survive rain, mud, and collapse.
Culebra Cut was the hardest part, a long wound carved through the hills.
The canal was not a single cut, band. It was the beginning of a whole system of water control. In the heat and rain of Panama, the canal was being carved out of jungle and mud, one load at a time. The cut grew deeper, but the hills still had to be broken apart.
Every foot of that cut had to survive rain, mud, and collapse. Culebra Cut became the hard middle of the canal, the part the jungle would not give up easily.
The canal was not just a trench tunnelate. It was the first great wound that would connect two oceans.
In the heat and rain of Panama, the canal was being carved out of jungle and mud, one load at a time. The canal was no longer only a cut through the land, it was becoming a staircase for ships.
Each lock chamber had to hold back the sea, release it, and raise the ship in stages.
The lock was a machine made of concrete and water. The Panama Canal was becoming a staircase of water, stone, and steel.
In Panama, the canal was no longer just a cut through the earth. It was becoming a living system of locks.
The locks did not pump ships upward, Tern said. They used gravity, gates, and carefully controlled water. This was the canal's greatest trick, Kendick, lifting a ship with water, then lowering it again on the other side.
At last, the ship was crossing the isthmus, one chamber at a time.
The canal had learned how to move ships, but not across water, but through it. The canal was no longer a construction site, Joy. It had become a living passage between two oceans. Every ship crossing Panama had to climb, pause, and descend through a machine of water.
Panama did not build a bridge over the continent, it built a staircase for ships through the continent. In
At last, the two oceans were joined by one of the greatest passages ever carved by. They built a machine deep under the ground to study the first moments of the universe.
Above, the city stayed quiet. Below, a ring of steel and concrete waited for particles moving near the speed of light.
The world above looked ordinary. The world below would become one of the largest scientific machines ever built.
To build the collider, engineers first had to open a way down into the planet. Before the machine could probe the universe, engineers had to carve a hidden world beneath the ground.
To build the collider, engineers had to open a path from the surface to the underground ring.
What looked like a simple hole in the ground was actually the doorway to a machine dozens of kilometers across.
On the surface, life looked normal. Below it, the machine was slowly taking shape.
The tunnel was no longer empty. It was becoming a precise circle of science under Switzerland.
The machine was still hidden, but the underground ring was now real. The tunnel was ready. Now the machine itself had to be lowered into it, piece by piece.
Every magnet had to sit in the ring with extraordinary precision. It counts, or the particles would never stay on course. Inside the ring, everything had to be almost perfectly empty, so particles could race without being disturbed.
A time-lapse view reveals the accelerator ring. Superconducting magnets and cryogenic lines snake through the tunnel, maintaining the extreme cold required for operation.